In this video, we will learn how to solve decision-making problems in artificial intelligence using the Minimax algorithm and alpha-beta pruning. Let's dive in.
You know, it really all comes down to a concept we call adversarial search. Just think about games like chess or even tic-tac-toe. You've got two players, right? And they have completely opposite goals, each one competing to win. Well, these techniques give an AI a solid strategy to find the absolute best possible move, all while assuming that its opponent is also playing their best game.
So, here's our game plan. First, we'll cover the basics of adversarial search. Then we'll walk through solving a problem using the Minimax algorithm. After that, we're going to look at a really cool optimization called alpha-beta pruning, compare the two, and then wrap up with why all of this is so important.
So, what's actually happening under the hood when two AIs, or maybe an AI and a person, are facing off in a game? Well, the answer is in this thing called a multi-agent environment, which is really just the arena where this whole competition happens.
And this is the core idea right here. We've got two or more players. In AI, we call them agents, and they have conflicting goals, all happening in the same space. Now, we're going to focus on a specific kind of game called a zero-sum game. And that's just pure competition. One player's gain is exactly the other player's loss.
All right, let's jump into our first tool for figuring out the best move in these games. It's a really foundational algorithm, and it's called Minimax.
Take a look at this game tree. This is what we're going to solve. Up at the top, we have our max player, the maximizer. Their goal? Pretty simple. Get the highest score possible. And the levels below alternate with the min player, or the minimizer, who's always trying to force the lowest score possible. Those numbers at the very bottom? Those are the terminal values, the final scores of the game.
You know, the logic here is actually super straightforward. We're going to start at the bottom and just work our way up. Min players will always pick the smallest value they can get. And max players, you guessed it, they always pick the largest. We just keep passing these choices all the way back up to the top.
Okay, let's put this into practice. We start at the bottom layer. Node D here is a min node, and it can see two children with the values -1 and 4. So it's going to choose the minimum, which is -1. Makes sense, right? Following that same logic, node E chooses 2, node F chooses -5, and node G chooses 0. And just like that, we've assigned values to that whole layer.
Now let's move up one level to nodes B and C. These are max nodes. So node B looks down at its children D and E, which now have the values we just figured out, -1 and 2. Since B is the maximizer, it's going to choose the highest value, which is 2. And over on the other side, node C looks at its children, F and G, with values -5 and 0. So C chooses the maximum, which is 0.
And for the final step, we're back at the root, node A, which is a max player. It looks at the values from its children, B and C, which are 2 and 0. To maximize its outcome, A is going to choose the highest value, which is 2. So here's the key takeaway. The optimal outcome for the max player is 2. The Minimax algorithm has found our best possible move. So Minimax works perfectly, but it's got one huge drawback. It explores every single possible move. For a simple little game, that's totally fine. But imagine a game like chess. That becomes computationally impossible. And that's where our next technique comes in. It's a really brilliant optimization.
The whole goal of alpha-beta pruning is to get the exact same result as Minimax, but to do it way faster. It does this by intelligently ignoring, or pruning, entire branches of the game tree that it can prove won't have any effect on the final outcome.
So how does it do this? Well, it uses two variables, alpha and beta. Think of alpha as the best score, the highest value, that the max player is guaranteed to get so far. It starts at the absolute worst score, -infinity. And beta is the best score, the lowest value, that the min player can force. It starts at the best possible score, +infinity. And here is the magic rule that makes this whole thing work. As the algorithm goes through the tree, it keeps updating alpha and beta. And the moment that alpha, which is max's best guaranteed score, becomes greater than or equal to beta, min's best guaranteed score, we can just stop. Why? Because it means that one of the players has already found a better move somewhere else in the tree. We can just prune that entire branch and not waste any more time on it.
All right, let's see this in action. We're going to trace the algorithm on this new tree. Now remember, we go from left to right, depth first, and we're always updating and comparing our alpha and beta values at every single node.
Okay, let's trace this carefully. We start down the leftmost path.
The first min node sees values 10 and 5. It chooses the minimum, 5. So that value gets passed up to its parent, a max node. Now we go up one more level to a min node. It knows that its left path results in a 5. This becomes its best option so far, so its beta value is now 5. Now that min node explores its right side. The max player there finds a value of 7. At this point, the min player compares, okay, my best option is to force a 5. This new path leads to a 7. Since I want the lowest score, 5 is obviously better. The max node below it has found a 7, which is already higher than the parent min node's beta of 5. The min player would never let the game go down this path, so there's no point in exploring it any further. We can prune the rest of that branch. We call that a beta cut.
Now for the second prune. So after checking out the entire left side of the tree, let's say the root max player knows it has a path that guarantees a score of at least 8. So the root's alpha value is now 8. That's the score to beat. We pass this alpha value down as we explore the right side. We go all the way down and we get to a min node. It looks at its first child and sees a value of 7. Now we check our rule. This path offers a 7. But wait, the max player at the root is already guaranteed a score of 8. That's its alpha value. Why would the max player ever choose a path that's leading to a 7? It wouldn't. Since this current value, 7, is already worse than an option max has already found, we don't even need to look at any more children of this min node. We make an alpha cut and prune that branch immediately.
Okay, so let's put these two head to head and see how it all stacks up.
The takeaway here is actually pretty simple. Minimax is thorough, but it can be incredibly slow because it has to check every single node. Alpha Beta is smart and efficient. It gives you the exact same optimal answer as Minimax, but because it prunes all those branches that don't matter, it gets there a whole lot faster.
So, after all that theory, what's the big picture here? Why should you care about any of this?
Here's the core idea that ties everything together. Minimax gives us the perfect, unbeatable logic for playing against a perfect opponent. But alpha-beta pruning is what takes that theoretical perfection and makes it practical. It makes it fast enough to actually power real-world applications. And these fundamental techniques aren't just for textbooks. They are the backbone of tons of AI game-playing systems, from simple games like tic-tac-toe all the way up to incredibly complex strategy games like chess. This is literally how an AI learns to think strategically.
And that kind of leads to a final thought. We've applied this to games, right? But this idea of competing agents with conflicting goals, that applies to so many other areas, like economics or negotiations, even military strategy. It really makes you wonder, what other complex decisions could be modeled and maybe even solved as a game?